So today we're going to do the toughest part of Chapter 5. And the rest of Chapter 5 is not so bad. But the sheet I handed out to you has what's called the laws of exponents in there. And we need to have that so that we know what we have going on with those. And so we're going to walk through all these. These are in sections 5.1 and 5.2a is where we're going to find these different laws and different properties that we use with exponents. And so if we look at the very first one, it's the product rule of exponents. And what that means is that we have a to the mth and a to the nth. But the key piece here is the bases are the same. So my bases match each other. So they're identical to each other. So a and a. So what I can do based on my law of exponents, it says if the bases match, which they do, I can take my exponent piece and add those together. So my exponent piece says I can take m plus n and end up with what that value happens to be. So if you go over to the example, x to the 5th times x to the 6th, 5 and 6 are the exponents, base of x, so they both match each other. So since they match each other, that means I can simply add my exponents together at the top. So I have x 5 plus 6, or my answer ends up being x to the 11th power. Now why this works is that if you expand these two out, x to the 5th means I have x times x times x times x times x, or I have representing that base 5 times itself. We got that? And because we've got that base as being, or the base is x, the exponent was 5, that means I want to see x times itself 5 times. X to the 6th means I have x times x times x times x times x times x. And so what's happening with those is if I look at this, how many x's do I have up here? Well, I have a total of 11 x's. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So that's why I can just simply take my exponents and add them together. So another example might be y to the 7th times y to the 3rd. What would my answer be then? So it's going to be y to the 7 plus 3 is, of course, 10. And so we end up with y to the 10th power is what I happen to have with that. Get rid of this thing. Okay, so y to the 10th power. So you think you got that one? And we're going to play around and do some more stuff with these as we go through. So if we took that one and maybe expanded it out here, and we did x to the 3rd, y to the 3rd, times x to the 4th, y to the 3rd, what would my answer be if I had that as my problem? Well, I would go through and look at my x's, and I can combine or add the exponents together. So 3 plus 4 is x to the 7th. Y to the 3rd and y to the 3rd bases match. So 3 plus 3 is y to the 6th. We good there? Okay. So basically all you're doing is going through and looking to see what kinds of combinations and what kinds of stuff you happen to have. Another way of looking at this, and they can put numbers in here. And you might see them looking like that as your problem that you're going to see. The only thing that we have to do different than the one up above is I need to multiply my numerical parts. So 3 times a negative 3 is a negative 9. X to the 4th and an x. Now this x has what kind of exponent on it? A 1, yeah. So x to the 4th and x to the 1st is 4 plus 1, or x to the 5th. And finally, y to the 7th and y to the 4th will leave me with y to the 11th. Okay? So these are my combination pieces in there, and so I want to make sure that I have that in place, okay? So I need to be careful with that one, and that's what that law does for me, is it lets me combine stuff. So then if I go to the next one that's listed here, power of a product rule, this is saying I can distribute or give each exponent within that problem that same n, or it's a distribution like we've been doing and distributing it, making sure you give it to everybody in there. When we talked about distributions quite a while ago, we said it was kind of like giving kids ice cream, because you got to make sure you get every kid ice cream, and in here I got to make sure I give every exponent an n when I work with that, and so that's what I end up with. If you look at this one over here as my example, what would my answer be? So it would be 3 times 3, or x to the 9th, 3 times 2, and y to the 6th. So I'm multiplying here. So it's a multiplication. Or another way of looking at this one is if you expand it out, this 3 means I want to see x to the 3rd, y to the 2nd 3 times. And if you expand it, then I can use my rule I just talked about up above. X to the 3rd, x to the 3rd, x to the 3rd is x to the 9th. Y to the 2nd, y to the 2nd, y to the 2nd is y to the 6th. So I can end up taking that one and adding some additional pieces to it and coming up and expanding that one out. But again, my shortcut is to distribute that by any exponent that there happens to be. So further examples of that one might be x to the 3rd, y to the 7th, raised to the 4th on the outside. So if I do this one, I gotta give everybody a 4. So 3 times 4 is x to the 12th. 4 times 7 is y to the 28th. Does that make sense? Okay. We good? You got questions with that one? So it's just kind of distributing. Now if you have a number out in front, 3x y to the 5th raised to the 2nd, everybody, including the 3, gets a 2. So don't leave an exponent off and not multiplying it by. 3 is to the 1st power, x to the 1st. 2 times 1 is 3 squared. 2 times 1 is x squared. 2 times 5 is y to the 10th. So then 3 squared is 9, x squared, y to the 10th. So you need to square out the numerical parts in here. Don't leave them unsquared, or don't leave them multiplied out with whatever your power happens to be. So you want to make sure that you do that. So you get these pieces multiplied out, and don't leave your numbers just with your piece on the front of those. So here's one more. Let's see what we can do with this one. A negative 2, x to the 4th, y to the 3rd, z squared, all raised to the 3rd power. So what would that one come out to be? What was it?
Z to the 2nd.
Yep, z to the 2nd. That is a 2. So I'd have a negative 2 to the 3rd, x to the, what? What would x to the 12th? Y to the 9th, z to the 6th. But I can't leave my negative 2 not multiplied out. So negative 2 times a negative 2 times a negative 2 is a negative 8, x to the 12th, y to the 9th, z to the 6th. Okay? So not too bad. It's just keeping the rules and keeping them in their correct spots, because eventually we'll stick them together and you'll have some combinations of things that we need to do. So if we go down, this was rule 1, rule 2, Rule 3, so we keep our notes together. In Rule 3, we have a quotient. Quotient means, of course, divide. So we need to do the exact same thing as we did with the multiplication, but here I'm raising something to the nth power, but I still distribute it, and I give it to each one of these. So I have a to the nth over b to the nth, meaning my bases are different, and so I just distribute that. So then same thing over here, 2 times 3, 2 times 4. So I find that this one is x to the 6th all over y to the 8th. Also, this 2 means you could have seen this separately. And then I would have just still combined using my rule 1, and x to the 3rd and x to the 3rd is still x to the 6th. Y to the 4th and y to the 4th is, of course, y to the 8th. And so we end up with getting those for our solutions to that. Okay? Yes or no? Seems like it's going to work. Okay. So that one expanded out. So if I had the 3rd rule in here, x to the 4th, y to the 2nd, all over z to the 5th, raised to the 4th outside. What would I get for an answer to that one? It's just distributing each thing out. So I find I have x to the 16th, y to the 8th, that's a 2, and z to the 20th, and that's my answer. So all I did again is gave each piece its own part. If you add numbers in, 2, a to the 4th, b to the 3rd, over 3, c to the 4th, raised to the 2nd power outside. What will that come out to be? We're kind of getting all these rules along at the same time and expanding them out some. So treat it like it's 2 separate pieces. So I have to square my 2, which is 4. A to the what? Well, a to the 4th raised to the 2nd is going to give me a to the 8th. B to the 6th all over 3 squared is going to give me 9, and c to the 8th. Okay, so not hard. These aren't too bad. It's just that you got to remember that you're distributing and giving, and you got to give every piece that number or that value that's on the outside. So don't forget somebody, because if you forget somebody, that means your answer won't be correct. So you want to watch that and make sure that you get your pieces in the right spot with it. The quotient rule. Quotient, again, division, rule of exponents, means that if I have like bases, these are like bases. The one up above had unlike bases. Notice it was A and B. This one is just plain straight A. But because they are like bases, that means I can take the exponents and subtract them. So I can take m minus n to get my answer. The reason this works is if you take our example over here and expand it, x times x times x times x times x, and I need 7 of them. 1, 2, 3, 4, 5, 6, 7. And put that over x to the 3rd. What is really happening with this is that things are canceling out. But instead of writing it out longhand and canceling everything, our rule says we can just take these 2 and subtract them. So I still end up with x to the 4th power, and that's what I had over here as well, because I only have 4 x's left. And so I get x to the 4th power. So these guys subtract. And so I get a difference between them. All right, so it's a subtraction taking place there when we work with this type. So let me flip my page over here. Getting kind of tight down there in the bottom anyway. Number 4, I'll give you an example of a number 4. So if I said I had x to the 5th y to the third all over x y to the second. What would my answer be? So, because I'm going through and subtracting exponents, 5, the base of x match, so 5 and a 1, because that's what's here. 5 minus 1 is x to the fourth. Y to the third and y to the second is just plain ordinary y. Now, do I need my 1 there? No, because it's looked at to be that. In intermediate algebra, we use this section, these two sections, 5.1 and 5.2 as review, because we start working with it with fractions in there, because we have a whole section that's on radicals, and we end up taking these things and we have fractions in here instead of whole numbers. And so we still use the same rules that apply. So that kind of gives you a hint for next semester if you go on and take intermediate algebra. But it's still going to be used in there as well. So how about this one? 4, a to the third, b to the fifth, all over 2, a to the second, b to the fifth. What would my answer be out of this one? Numerically, it works like it's a fraction. So 4 over 2, what's 4 over 2 reduced to? 2. A to the third and a to the second leaves me with an a. B to the fifth and a b to the fifth, 5 minus 5, long gone. Okay, I don't have any b's left. So my answer is just simply 2a for that one. So you're going to go through and you're going to look at these and do them piece by piece. Don't try to rush in and do the whole thing all at once, because you got to work out each separate section within that. So what do you think of that one? We're okay or not okay? Question?
The numbers don't have to be the same to use that rule.
Nope. No. The numerical part is reduced. The numerical part is not taking the exponents and subtracting them. The bases here, the variables, are the only things we subtract exponents with.
Is that what all these rules just change the variables?
Usually, unless you have something raised to a power. Now, if we had looked at and had a power, if we had 3 to the fourth, a to the fifth, b to the second, all over 3 squared, a squared, b, if you had this, for instance, then your numbers are acting like bases. Notice it's 3 and 3, so now they're acting like a base, so then I could subtract them. But when they're straight numbers like 4 and 2, you're only looking at what you can reduce in it. Okay? So we would reduce stuff in here, but over here, because, well, they don't cancel. You got to look at your exponent. So 4 and 2. So really, I still am left with a 3 squared, because 4 minus 2 is 2. So now 3 is acting like a base. No, you can't do that, because now it's acting like a base. Now it's acting like an A or acting like a B. This is the base of my exponent, because now it's raised to a power. This wasn't raised to a power. This was just plain old straight 4. And this was just plain old straight 2. So since 2 goes into 4, I can reduce it and get 2. All right? But otherwise, these have to act like exponents. So 4 take away 2 is 2. Yes?
What if, say, the bottom three didn't have the exponent?
Then it would have been 4 minus 1.
Okay, so
Okay? Okay? Because then my exponent, if there's no exponent, there's a 1 there. Yep. And good question to ask, though, because it does make you wonder. But you can't just cancel these 3's and leave these exponents just hanging out there. Okay? They're connected to those, and so you have to go through and cancel some stuff out. Yep. Okay. So finishing this one, a to the fifth and a squared gives me an a cubed. B squared and a b to the first power. If there's no exponent, there's a 1 there. So b2 minus 1 gives me a b. So my final answer is that. But then I need to take care of this exponent. So 3 to the second power is really 9, a cubed b. So I need to multiply that 3 out. not leave it as an exponent. So you have to multiply it and come up with what its value would end up being for those. So you'd want to watch that and make sure that you get your stuff in there, okay, in working with those. So we think we're good with 4, rule 4? Okay. Rule 5 is a 0 exponent. So if I have a to the 0 power, it's equal to 1. So any base except 0 raised to a 0 power will equal 1. So it's always going to equal 1. No matter what it happens to be, it's going to equal 1. So if I end up with x to the 0 power as my example, it's equal to 1. If I had 392 to the 0 power, it's still equal to just plain old 1. Okay? So whenever you got a 0 power, that means it's equal to 1. So if you look at these for examples, so if we go number 5 here with examples, if I had 3x to the 0, y to the 0, what would my answer be? Well, x to the 0 is 1. Y to the 0 is 1. So really, the only thing I have left is 3 times 1, or just plain old 3. Okay? Because the 3 was not raised to a 0 power. They do in here give you things like x to the 0 power plus 3y to the 0 power. What would my answer be to this? So x to the 0 power is 1. 3, y to the 0 power is 1. So I get 1 plus 3. So 1 plus 3 is, of course, 4. And so I end up with 4 for my answer to this one. Okay, so 4 comes out to be what that value happens to be. So sometimes you got a mathematical problem, and they usually do that with these things to the 0 powers that are in there. How about this one? 7 x to the 4th, y to the 0, z to the 5th. What would my answer be to this one? So 7 doesn't have anything on it. X to the 4th still has to stay. Y to the 0 becomes 1, so 1 times anything is what you have. Z to the 5th power is z to the 5th power, so that becomes my final answer. It's just simply that whole thing. So 7x to the 4th, z to the 5th will be what I have for that answer to this one. And if you go back to our rule where we distributed right here, so if I had x to the 4th, y to the 3rd raised to a power of 0, that means 0 gets multiplied by everybody. 0 times 4 is 0. 0 times 3 is 0. So my answer is just simply 1 because it takes care of those. All right? That makes sense? So watch those 0 exponents. If they pop up in there, they're big old fat ones, okay? So you get a 1 out of what you happen to have with those. These last two are negative exponents. If I get it to where it's not wiping out and making it all white. So they're saying that the main thing with negative exponents is the exponent moves or switches places and becomes positive. So it's going to switch where it's at, and it's going to become positive if we deal with a negative exponent. So if it's a to the negative nth, it becomes 1 over a to the positive nth. If it's 1 over a to the negative nth, it becomes in the top and becomes a to the positive nth power. And so it's just moving it and switching places. So whenever you run across a negative exponent, take it out of where it's at, move it to the opposite location. So if it's in the numerator in the top, like my example of x to the negative fourth, it's going to become positive and go to the bottom. If it's in the bottom and it's negative, it's going to go to the top and become positive, and so you get x squared, y squared. So it's just moving and switching places whenever you've got a negative involved. So we're going to move it around and get it to a different location within that. So let's see what we can do with some examples of these. So in 6, if you have x to the negative 7th, y to the 3rd, all over z to the negative 2nd, what's going to happen with this problem? So the only thing that happens is anything with a negative exponent goes to a different location. This exponent is going to go to the bottom and become positive. Y to the 3rd is already positive, so it doesn't move. Z to the negative 2nd is negative, so it's going to move from down here to the top. And so it switches places. So they just move from one location to another location within those. So you want to get them moved around to wherever they happen to be within it. Okay, so here's another one. Negative 2, a to the negative 4th, b to the 2nd, all over a to the 5th, b to the negative 3rd. So we've got some negative exponents in there. So in order, before I ever start working on anything within this problem, I know I got to move some stuff around. Does the negative 2 move? No, it doesn't move because it's not an exponent. Okay, only negative exponents. So negative 2 stays where it's at. Where does a to the negative 4th go? Where does b squared? Stays. A to the 5th on the bottom stays in the bottom. B to the negative 3rd moves to the top. And then I need to go back and look at my problem because now I've got to use rule 1 that says I have like things, so I need to combine some stuff. So b squared and b cubed becomes b to the 5th. A4 and A5 becomes a to the 9th. And I'm done. Okay? So stuff has to move. So you got to switch some things around in some of these and get them to where they're positive with what you happen to have. If we go back to that quotient rule where we had like bases, and that's rule number 4, and you have 3x to the 5th, y to the 7th, all over 6x to the 9th, y to the 3rd, and we use our quotient rule. Quotient rule, of course, says I got to reduce, so 3 and 6, do they reduce? 3 goes into 3 once, 3 goes into 6 twice. X to the 5th and x to the 9th, they're both bases match, so now I got to do some subtraction. So 5 minus 9, so 5 minus 9 leaves me with x to the negative 4th. We good there? 5 minus 9, so negative 4. Y to the 7th, y to the 3rd, 7 minus 3 is y to the 4th. But I can't leave this problem looking like this. I can never leave a negative where it's at. It has to switch places. So it's going to move to the bottom. The y to the 4th stays on top. The 1 I don't really need, but I need the 2. So this becomes my solid answer. Okay? So I have to make sure I move that. Or if the exponent on like bases is bigger in the denominator, subtract in the denominator, and leave it there. Oh, I got music today. So notice 9's bigger than 5. So if I take 9 in the bottom and take 5 away from it, I would leave my x to the 4th in the bottom, and I wouldn't have to write it the separate way in the center. But if you don't remember it, just write it in the center and see what you get with that part. Okay? So do make sure that you're careful with those and work them out. Let's do another one of those. Yes?
Kind of confused on what you do with the numbers there, the 3 and 6.
It's acting like a fraction. If that's all you had.
Oh, you're just
Yeah.
simplifying it?
If that's all you had, then all you're doing is reducing it. Because if you reduce this, 3 goes into 3 once, 3 goes into 6 twice, so all I did was reduced it.
Then how come the 1 disappears in your final answer?
Because I don't really need it there. It's just kind of an extra thing that I don't have to have. Yeah. Yeah, I don't have to have it there because it's just another part of what I have, so I don't really need it. Okay? Yeah. So it's not a necessity that I have to have there. Okay. Let's do another one of these. It's got some additional subtraction stuff to take care of negatives in it. So if I had 4, x to the 3rd, y to the 7th, z, all over 2, x to the 5th, y to the 4th, z to the 7th, what would my answer be? So you're kind of looking at it in chunks. So we're looking at 4 and 2. What happens to those? Reduce. 4 divided by 2, because they both reduce. 2 goes into each. Gives me a 2. Then I'm moving to my x's. X to the 3rd over x to the 5th. So 5 take away 3, because 5's bigger in the denominator, leaves me an x squared down below. 3's smaller, 5's bigger, so 3 from the 5 in the denominator leaves me an x squared in the denominator. If you can't remember that, you can always leave it up top. 3 minus 5 is x to the negative 2nd, so you can still leave it there if you need to, okay? And then flip it later, okay? Y to the 7th, y to the 4th, 7 take away 4 is y cubed. And then z to the 1st, z to the 7th, 1 minus 7 is z to the negative 6th, or if you know it's bigger in the bottom, 7 minus 1 is z to the 6th, and you're all done. So then if I move them, 2 stays, x to the negative 2 needs to go to the bottom, y cubed stays, z to the negative 6 needs to move and go to the bottom. So I get the exact same answer. It's just that if I can remember that I've got bigger things in the bottom and do my subtraction down there, I will end up getting the correct answers out of those. So it's just remembering where they're at and what position certain things hold. Okay, so negatives got to move and switch around. So that's kind of all of our rules that we have with these. And there really isn't any other ones. They cover them a little bit. They might do them in different sections within it. So let's go and pull back and get some of the actual questions that you guys will run across in these sections. So we've got the rules down. So now we got to go through and we need to take a look and see if we can fix some of these. So if they gave us just simply 9 to the negative 1st power, what would my answer be? Yep, 1 over 9 or 1/9. So it would just move it and switch it. So what if I had 2 times 3 to the negative second power. 2 has a positive exponent, so it stays. 3 to the negative second, where does it go? To the bottom and becomes positive. So I have 2 over 3 squared, which is 2/9. So you're going to move it and get it into a different location there that you happen to have with those. Okay, so that's what happens in that situation. Another one. What if we had 5x to the negative third, y to the third, times a negative 7, x to the 0, y to the third? What will happen with this whole thing? So it's kind of sticking all of our different pieces. We got like 3 different rules going on in here. And you take care of it in chunks. You take care of it with what matches. So numerically, I've got 5 times a negative 7. So what's that going to give me? I have x to the negative third and x to the 0. Well, what do we know about x to the 0? That's good old 1, right? So where does this go? X to the negative third on the bottom and becomes positive. Then we're left with y to the third, and y to the third becomes y to the 6th. Yep. So you got a bunch of different rules. We had the negative exponent piece in here. We have the rule of something raised to a 0 power, and then we had the product rule because we had some multiplication with exponents involved. So we had 3 rules going on in that one particular question. So we have to be careful and make sure we get our stuff where it's supposed to be. How about this one? Negative 2 to the second power times a negative 2 to the second power. Like bases. So what am I going to end up with? These 2 match. Rule says add exponents. But it's numerical, so I have to multiply it all out. So a negative 2 times a negative 2 times a negative 2 times a negative 2. Or an even exponent on a negative makes it positive. So 2 to the 4th power, 2 times 2 is 4, times 2 is 8, times 2 is 16. So my answer is just plain 16 with that one. So you've got some multiplication stuff. How about this one? 3x to the negative third, y to the negative 4th. So what will we be left with? Again, piece by piece. So 3 stays. X to the negative third is going to do what? Bottom. Y to the negative 4th goes to the bottom. And that's my final answer. Okay. So that's what I would type in. So I'd hit my fraction bar, my fraction key on my keypad, put my 3 in, put my x to the third and my y to the 4th in, and we would be good to go. And so that would be what my answer would be with that one. How about this one? 12x to the third over 4x to the 7th. Yep, 3 over x to the fourth. 12 divided by 4, reducing the numerical part. 4 goes into 12 3 times, 4 goes into itself once. X to the third and x to the seventh, you can say 3 minus 7, giving x to the negative fourth, which still needs to move, or subtract in the bottom. Do 7 minus 3 and get your 4, and leave it in the bottom. So we end up with 3 over x to the fourth. Okay, with that one. I think that's pretty much the gist of what they end up giving you in this. Here's one more. 5 to the 9th over 5 to the 8th. What would I be left with? So 5 to the 9th and 5 to the 8th. They're dividing each other. So what would I have to do to my exponents? Bases match. Exponents get subtracted. 9 take away 8 leaves me with just simply old 5. So I get just a regular 5 with that one. So 5 becomes my value that I happen to have. Okay? Yes? Good with that part? That's 5.1. That was the laws and stuff they have in there. 5.2 is broken into 2 parts. 5.2a is doing some more stuff with these. Still the same rules. It's just using maybe a different combination of those and sticking some stuff together. They get into x squared raised to the fourth, and we talked about that. So that's just a distribution. 4 times 2 is x to the 8th with that one. How about y to the negative 7th raised to the 2nd power? What's that one's answer going to be? Yep, 1 over y to the 14th. Perfect. Yes. Yep, because it moves that whole thing. How about 5x raised to the 3rd power? Five x cubed? What has to happen to the 5? Remember, everybody's got to get that ice cream of 3. So you got to have 5 cubed, x cubed. But what's 5 cubed? What's 5 cubed? Put that on your calculator. It's 125, yeah. If you put it on your calculator, you're going to hit 5, your caret key, a 3, and you'll end up getting your 125 out of that. And then bring your x cubed down. So don't forget to get your x cubed in there with that one. And making sure you get your distributions in there. How about this one? 2y all over b, or 2y over b, yeah, that'll work, raised to the 9th power. Oh, should be a 4th power. Let me get it smaller, as my 2 will get really big if I make it real big. And don't forget that everybody in here needs a 4. Don't leave somebody out, because if you leave somebody out, they catch up with you. So you want to make sure that you get those in there. Okay. Then they give you this one. 2x over y to the negative 3rd power. So if we multiply by a negative power on the outside, what's going to happen then? Same thing. Yep. Just that when we get all done, we need to be careful because you got negative exponent. So all that means is those all got to switch places. 2 goes to the bottom and becomes a positive exponent. X to the third, negative third goes to the bottom. And y to the negative third comes to the top. So I have y to the third over 2 cubed is 8, x to the third. So they basically switch places. So it's that distribution and making sure you get your signs in there and get all that distributing stuff done within those. Okay, this one's kind of got a whole bunch of stuff into it too. 6m squared, m cubed, n to the negative first raised to the negative third, all over 7 m to the negative second n raised to the negative first. So you've got double distributions going on. So we've got a distribution of a negative 3 times everybody at top. So a 6 to the negative third, m to the negative ninth, n, what's n going to be? Negative 1 times a negative 3 is a positive 3. The bottom, 7 to the negative first, m, negative 2 times a negative 1 is a positive 2, and n to the negative first. So now I got to switch some stuff around. I gotta get rid of all those negatives. So 6 to the negative third goes to the bottom. M to the negative ninth goes to the bottom. N to the third stays up here. 7 up top. M squared stays on the bottom. N to the negative first goes on top. And so my final answer is 7. N to the third, n to the first is n to the fourth. 6 cubed. 6 times 6 is 36 times 6 is what, 216? Is that right? 216? Okay. 216. M to the ninth and m squared is 9 plus 2, or m to the 11th. So you've got a lot of reducing and a lot of changes going on in that one. So make sure you put these stuff on paper when you go through and do them. So that's kind of one of the tougher ones that may be in there that you need to do. Okay, let's keep going. So 5-2 gets a little bit harder than what you did in 5-1. How about this one? 2x to the negative third, y to the negative second, all over y to the third, raised to the second. Like little mysteries inside of them. You got some changing of stuff and moving a few things around. So hopefully that's what you ended up with. When you square the 2, you get 4. X to the negative 6 goes to the bottom. Y to the negative fourth goes to the bottom. 6, y to the 6 stays in the bottom. Then you just need to combine like things. X, y4 and y6, and we y10. And so we end up with what our solution happens to be to that one. How about this one? 2 to the third, m to the third n, all over n squared, raised to the negative second. So stick that on your paper, see what you end up with. So what happens on this case? We go through. First, distribute everything by -2. Get all that done. Adjust pieces. 2 to the -6 goes to the bottom. M to the -6 goes to the bottom. N to the -2 goes to the bottom. N to the -4 moves from the bottom and comes up on top. So we get it to a yes.
Probably didn't move it to because it wasn't a base.
It is a base. It's acting like a base because it's got a -6 on it. It's acting like a base here, 2 to the 3rd power. Okay? Yeah. Yep, it's acting like a base here. It's not a solid number. Okay? So it moves. And so it gets a different location. It's just if it were a solid straight -2 just sitting there, then it would not have moved. But it's moving because of this exponent in there. So n to the 4th and n squared means I have an n squared left in the top. 2 to the 6th power is 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32, times 2 is 64. And then I'm left with the m6 on the bottom. And so that becomes my solution. It's a lot of being careful and making sure you write down what you should. When you do these, double check and make sure you got your distributions done by everybody. And get your cancellation stuff to work in there. So how about this one? 5m to the 3rd times 2m to the -1st raised to the 3rd all over 14m cubed times 4n to the -1st. Oh, this is an n, sorry, my n in there. Not an m. These again are all the different types you run across in your homework. So your homework section's going to have a few in there. Make sure you go to practice. Don't hop right into certify with this one because it's kind of a thing you got to do some practice stuff with. 5m cubed doesn't change. This all gets a 3 on it, so I have 2 cubed and m to the -3rd all over 14n cubed times 4 n to the -1st. Might as well leave it in there. So up top, I have 5 times 8, because 2 cubed is 8, so that's 40. M to the 3rd is going to go, m cubed stays on top, but m to the -3rd goes to the bottom. 14 stays in the bottom, times 4. 4 times 4 is 16. 4 times 1 is 56. And n cubed stays in the bottom. And n to the -1 goes on top. So what comes out of this whole thing? 40 and 56 can cancel because 4 will go into 40. Well, let's see. I know I need to put 8 in there. 8 will go into 40 5 times, and 8 goes into 56 7 times. M to the 3rd over m to the 3rd cancels. n to the first and n to the third. 1 minus 3 is -2, or n squared in the bottom. So they come out looking kind of strange, but you got to maneuver all of your pieces around so that you get them in the right locations within that. So just be real careful with these things and watching what gets distributed. This 3 was not on this first part. It's only on the piece with the parentheses next to it. So it doesn't go way over here. It only goes to there. So watch where they put parentheses in these. Another one? You guys think? I think we'll do another one. Well, let's see what we got here. How about this one? You can see it. 3, a to the third, b to the -2nd, raised to the -2nd, all over 3a to the -2nd, b to the -1st. Again, signs are a big thing here too. So negative times negative makes it, of course, a positive. So be real careful with that as well. Yes.
3 squared on the bottom would go in 3 times 3 then.
Oh, you can. Yeah, because you could come up with 9 right here. But then 3 and 9 will reduce. 3 goes into 3 once, and 3 goes into 9 once. Or if you use your exponents, there's a 1. 2 take away 1, then the denominator leaves me with a 3 to the first. So you kind of got combinations of ways to do that one. So you could multiply it out, or you could leave it as it is and go from there. Okay. Did you guys get this? B to the 5th over 3a to the 8th, hopefully. Okay. One last one, and then we'll move on to other things. 5a to the 3rd times 2a to the -1st raised to the 3rd all over 8b squared 5b to the -1st. Okay, what do you think? You'll get B, 1 over B for that one, hopefully, as you're working through it. So that's the key to this part. So again, just be real careful. Remember, negative exponents move. They switch from where they're at, like this a negative 3 move to the bottom, and anything in the bottom that's negative moves to the top. And then you end up putting your rules together when you work with those. Okay, let's take a break, and then we'll come back and do 5.2b, which is scientific notation. All right, let's finish it up. So 5.2b is scientific notation. You guys dealt with scientific notation before? Probably. Scientific notation is used to write little bitty teeny tiny numbers into a way we can work with them, or taking really, really, really big, huge numbers and getting them so that we can work with them. And what it involves is when you get all done, your number is going to be in that format, meaning that there's only going to be one number in front of your decimal. So one number in front of the decimal. And then you're going to have it times 10. 10 is because it's a base 10 number. And then you're going to have the exponent. And that exponent is how many places the decimal point was moved. And this will make more sense when we start going through some of these things. But this is scientific notation. So if we had a really great big huge number, such as 4, 6, 8, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, and that was a number that I wanted to take and use, that is a whole number. And it's very important that you pay attention to whether they're whole numbers or decimal numbers. So in decimal numbers, you'll have something that's very, 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 very small. And so you've got two varieties here. You have a whole number variety and you have a decimal variety. And the reason they're different is it's based on where you move your decimal point. So if I have this whole number and I want to turn it to scientific notation, my decimal point sits at the very tail end of my whole number. So in order to use my rule, I can only have one number in front of there. That means I have to have 4.68. So that means this decimal point needs to move all the way over so there's one spot in front of it. So if I move it all the way over so there's one spot in front of it, how many places did I move it? So then I write times 10, and I go back up here and I count how many spots did I move it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And so that 12 becomes my exponent on there. Okay, so if I've got a whole number, it's going to move it to the left. So it moves decimal point to the left. So I'm going to move it to the left. So if I'm going to take it from that spot, move it all the way over, and I get that for my answer. Okay? If, and it's a whole number, so this remains positive. So the exponent will be positive. So if I have a decimal number that's very, 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 very small, I'm going to move it the opposite direction. So it moves back this direction. So I still stick to my rule. One number in front of the decimal times 10. But now because it's moving to the right, my exponent on base 10 will be negative. And that's what takes and makes the difference between these two. So if it's a positive exponent, it's a whole number. If it's a negative exponent, it's a decimal. So how many places did I move it? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So I put a negative 13 on there as opposed to a positive 13 because that tells me if this is a decimal. That told me that was a whole number. Okay, so it's moving your positions from one thing into the other, and so that you get your different pieces in there. Okay, so let's do a few more of those and see if we can adjust some decimals. So if I had the number 3, 0.6100000000. And I want to write that into scientific notation. Move it over. So 3.61, that's the easy part. And then the other easy piece is just counting. 1, 2, 3, 4, 5, 6, 7, 8, 9. So I have times 10 to the 9th power. Okay? So it's just moving decimal points and getting them where they need to be within those. So if you had a real small number, and I want to turn that to scientific notation. So same thing, 3.9, count 1, 2, 3, 4, 5, 6, 7, 8 places, times 10 to the negative 8, because it is a decimal, okay? So that's turning regular numbers, regular whole numbers, regular decimals into scientific notation. We good there, you think? Again, just put that number with a dot with one position ahead of it and leave it there. Then it's to turn scientific notation into whole numbers or decimals. So if you start out with 8.39 times 10 to the negative 9th power, I need to look at that and know that what kind of number is it going to be? Will it be a whole number or a decimal? It's going to be a decimal. Yeah. So it's going to be a decimal. So now what that means is I need to rate 8.9 or 39 over here, but I need to move it back 9 places. So if I move it 1, that means I need to put 8 zeros in front of here. 1, 2, 3, 4, 5, 6, 7, 8. And then I've turned it back into standard notation, in other words. So here we're going to go from scientific back to whole numbers or decimals or standard notation. So I'm going to move it from one spot to the other. So I move it from one position to the other. So if I had 1.57 times 10 to the 7th power, I'd look at this one and I know because the 7's positive, that's going to be giving me a whole number. So that means I write 1.57 and move my decimal point back 1, 2, and then because 2 from 7 is 5, that means I need to put 5 zeros after that. And so I end up back with my whole number value. Okay? So it's just kind of moving decimals from here to there and bouncing back and forth within those. So you move it from one spot to the other and you get it back into whatever notation. Key piece, exponents. Negative decimal, positive is a whole number. So it tells you which way to move it. So if it's a negative exponent and I'm turning it back, I need to move it to the left. If it's a positive exponent, I need to move it back to the right. So I'm just kind of undoing what I did. We need to do more of those. Or you think you're good? Okay, because it'll ask you to bounce back and forth between these of moving from one to the other. Then the other piece that's in this section is that you need to be able to work with some mathematical problems connected to this. So one of those might look like 0.0015 times 570,000 all over 0.000019. So if this were my problem that I needed to do, if you went through Hawks and you went through their instructional piece, they would say turn all of these into scientific notation and work with them. So let's do that so we get an idea of what's going on here. So I need to move that back 3. So I have 1.5 times 10 to the negative 3rd times 5.7 times 10, 1, 2, 3, 4, 5. So So far, so good? The bottom, 1.9 times 1, 2, 3, 4, 5. Whoops, 10 to the negative fifth. And so then what they would do is they would take the numerical pieces, 1.5 times 5.7 on your calculator. So put 1.9 times 5.7 on your calculator. Divide that by 1.9. What was it? 4.5. Okay. Now, because I've got exponents in here, I can look at my exponents and take care of those like I did back in 5.2 or 5.1. And so negative 3 and a positive 5. What does that leave me with? So negative 3 plus 5, because they're in the top, leaves me with 2. 10 to the second. 10 to the second over 10 to the negative fifth. So that negative 5's got to come up top. So basically, if you just look at your 10s in here, you could put 10 to the third in the bottom, 10 to the fifth stays on the top, 10 to the fifth that's in the bottom becomes to the top. And so 5 plus 5 is 10. Take away 3, ends up being times 10 to the 7th power. So my answer is 4.5 times 10 to the 7th power. Okay? Now, not bad, but you got a lot of work in there and a lot of connections and a lot of stuff that you need to do. So we can also, with not doing it, put in scientific notation, we can just stick this whole thing on my calculator, just as it is. So if I stick it on my calculator, just as it is, I can go through, get my calculator on over here, I can go and put 0.0015 times 57000 divided by 0.0004019 and hit enter, and I get that. And if it asks me in Hawks to put it in scientific notation, I can do that too. Because now all I need to do is count back here, 1, 2, 3, 4, 5, 6, 7, and I ended up with 4.5 times 10 to the 7th power. Okay, so you don't necessarily have to put them into scientific notation in order to work with them on your calculator. So you can leave them as regular numbers and then convert your final answer back to scientific notation. Because it's going to ask you for scientific notation in there when you work with those. So you can do some converting stuff. So what about this one? What if we had this for a problem? 6.3 times 0.0006 times 50 all over 25 times 0.0035 times 800. Now, if I work this one out on my calculator, I need to put these pieces inside of parentheses, because if I don't, and I put this on my calculator divided by this on my calculator, it's going to take this number, multiply it all together, divide it only by 25, and take that answer and times it by each of these. That's not what it's asking. So it's asking to make sure you do all divisions with this thing. So on my calculator, if I stick it in here, I'm going to go parenthesis 6.3 times 0.40 times 50, close that in a parenthesis, put my division, another parenthesis, 25 times 0.0035 times 800, parenthesis, and hit enter, and I will end up with that for an answer. So I get 0.0027 or 27 thousandths. And if Hawk says scientific notation, I need to write it in. I write 2.7 times 10. I moved it back 1, 2, 3 to the negative third power. Okay, so on those, you don't have to necessarily put them into scientific notation to work with them. So you can leave them as non-scientific numbers and go through and work with them. If they give you a combination of one, like they do, for instance, this one, 5.2 times 10 to the negative 6 times 242 all over 7.4 times 10 to the 6th times 1.7 times 10 to the 3rd. You can turn that into scientific notation and then just follow your rules of what we've been working with and multiply the top two divided by the bottom two, then put your exponents together. Turn them back into standard notation and work with them that way, because this one would become 0.00000052. This one would become 7,4 with 5 zeros. This one would become 1,7 with 2 zeros. And then you can stick it on your calculator. So you can turn them back into non-scientific notation to work with them. Whoops, that got a little light. Pull it back down. Okay. Or if you want to stick them in scientific notation, above your comma key on your calculator, above the 7, you should have a comma key. There is an EE. Do you see that EE in there? So if I were going to put this thing just as it is into scientific notation, as it was here, I could go parenthesis 5.2, hit that second comma key to get my E in there. My E means it's scientific notation. Put in a -6 times 242, close that in parenthesis, divided by parenthesis 7.4 second EE 6. All I got to do is put the value of the exponent in there. I don't need to put the other part. Times 1.7 second, comma, 3. Close it in parenthesis, hit enter, and I get my answer. So my answer comes out looking kind of strange in there, but it's because of the division. But notice how it's got that little E and a -13. So this, if it was rounded off to the nearest thousandth, would be 1.0003 times 10 to the -13th power. And so that would end up being my answer to this question. Okay? So you can do it either way with those. So it's just kind of breaking them apart, seeing what ends up working out best for you with what you're doing. If you did it straight scientific, it'd be 2.42 times 10 to the 2nd power is what that would be. So then I would go parenthesis 5.2 times 2.42 parenthesis divided by, and only by numbers, 0.4 times 1.7 parenthesis equals. So I get that. Okay, that's what I had. And then just work with my exponents. -6 and 2 is a -4. So I have a negative, or 10 to the -4th on top, all over 10 to the 6th times 10 to the 3rd. So 10 to the -4th, 6 plus 3 is 10 to the 9th. The 4 needs to go to the bottom. And I get my -13. So either way that you work it out, we still get the exact same answer of putting it in a scientific or not putting it in a scientific. So use your calculators for that part. So you want to make sure that you get your stuff in there. Need to do more, or are you good? What do you guys think? Are you good? Or one more? One more. One more for the cause. They do give you, and I guess I should mention that, there is a story problem that pops up in this section. And I don't have it typed up because there's only one. And so if we look at this one story problem, and they're all the same, the single story problem that you'll run across will be this one, and that's what it'll always be. It says an atom of gold has a mass of 3.25 times 10 to the negative 22nd power grams. What is the mass of 3,000 of these? So basically, all you're doing is taking this scientific number and timesing it by 3,000. So when you go through and do that on your calculator, don't forget your EE key. So I can just put 3.25, second, my comma, negative 22, times that by 3,000, and I am good to go. So I get 9.75 times 10 to the negative 19th, and that's what I would end up typing into Hawks for my answer. So that's what you get with those. So that's the story problem type. So just realize that's just taking this and timesing it by that. If this is 1, I want to times it by 3,000 because I have 3,000 of them instead of only one of them. Okay? So that's what happens with that piece. Alrighty. One last one because I told you we'd do it. We'd do one more. So I'm going to turn that sideways. How about this one? 0.02 times 0.0027 all over 0.15 times 0.018. And again, use your calculator with it to get your answer. But also parentheses. Anytime you have more than one multiplication in the bottom, you need parentheses in there. So what will be your answer for this one? And again, if it asks you for scientific notation, turn it back because it comes out to be 0.02. Move it 2 back, and since I moved it 2 to the left, it's a negative 2, or 2 to the right, I should say, it's a negative 2. And so that would be my answer. Okay? So again, it's just a matter of typing it into your calculator and coming up with what they'd be. Okay? So that's that section. So again, these two sections, 5.1 and 5.2, A and B, tend to be, again, the tougher pieces that are in Chapter 5. So Chapter 5 is usually a pretty good chapter because we can, a lot of times you can check and make sure you did your answers correctly. All right, so that's that.